Focus up here. So what we're doing today and talking about today are parent functions and their transformations, and how the transformations can affect the graph or how the graph looks. So what we're describing is the change from the parent function to the new function that we have. Now there are four parent functions, well really three of these that we're going to look at. Linear, absolute value, and quadratic. And it's not that constant functions, we're not really going to look at them, there's not much that happens. It's either going to go up or it's going to go down. That's it. Because the constant function, a function is a part of the constant function if it's just a number. There are no variables, it's just one. Is the parent function. So you don't write this down. So f of x equals 1. Well, f of x equals 4 is also the constant function because it's just a number. And the transformation that would take us from 1 to 4 is, well, going up 3. We added 3. F of x equals negative 4. We subtracted 5. It went down 5. That's it. There is no other movement. It's just going to go up or down. That's all there is to it. So don't really focus on those there. Now, the other ones that we have are linear, absolute value, and quadratic. Linear is just a line. That's why we call it linear, line. Linear. Absolute value is our V shape, and it will have the absolute values. And our quadratic is a U-shaped graph, and we can tell that it's quadratic because of the square, the power of 2, the exponent of 2. And the quadratics will always have a U-shape, absolute value will always have a V, and linear will be a line. Now there are others. There's quartic or cubic. Cubic would be x cubed. Quartic is x to the fourth. We could have rational, because rational is going to be 1 over x. Then there's others. There's parent functions for all those, but we're mainly focused on these three here. These are the ones we're going to talk about. Now, linear, quadratic, and absolute value. There is a general form of each of these three here. So these three here are the general forms of each of the three. In the general form, we can plug in a value of a, h, and k and get the new version of the linear, quadratic, or absolute value with the given transformations. Also, if we're given a function that is a part of the linear, quadratic, or absolute value, we can know how the function was transformed or how it was changed to get to that equation there. Now the a, h, and k are going to have the same type of transformation, the same type of movement in all three. So the value of h, or h's value, where it's at, is going to have the same movement. K, for all three, is going to have the same type of movement. A is going to apply the same transformation for all three of these here. But I write them out for all three because they do look a little different, given it being quadratic, absolute value, or linear. So it's good to have a list of all three. All right. Now we will be coming back to this slide to write in what a, h, and k do as we get to it. Okay. Questions on this so far? Describing transformation. A transformation changes the size, shape, position, or orientation of a graph. So we're going to move it up, down, left, right, stretch, shrink. horizontal stretch shrink, vertical stretch shrink, reflect. Any of this here is a transformation. But specifically, the first one we're going to talk about is a translation. It's a transformation that shifts the graph horizontally, left or right, or vertically, up or down. It's either going to go left, right, up, or down. That is a translation, okay? But it does not change the shape, orientation, or size of the graph. We're just moving it on the graph. It's going up, down, left, right. It does not change shape, size, or orientation. Okay? Now, with this here, H is our horizontal, our left and right. Now, in past years, I've written it on all three, but it gets messy really quick. So I'm doing something a little different this year. So we can write underneath it, H is our horizontal. Back on the first page. So normally I would put left, right, and just draw an arrow to H and write it on all three. But I think that ends up getting to be a lot of written stuff writing around each of these three equations. So I'm just going to write it out underneath. I think it might be a little bit neater and look a little bit nicer if we just have them down below instead of drawing all three. Does that make sense? So because again, this horizontal translation will, H is applied to all three. That H value tells us the left, right. Now K is our vertical. Translation. Up, down, up, down. So horizontal translation is our H. If the value of H is positive, it moves to the right. If the value of H is negative, it moves to the left. Vertical translation. If K is positive, it goes up. If K is negative, it goes down. I don't know. I do not know. But they've always stuck with K, with vertical. I think it's more of a choice they use it for these here for algebra, because in trigonometric functions, they use a different one. I normally stick with K and H. H is connected to our X and horizontal. K is connected to our vertical. It might also be because V, especially in physics, is stuck with velocity. So there is some crossover. But there are places where they use the same letter for different things. Because here we do have A, but also A is signified as acceleration, which is different than velocity. But here, H, horizontal, left, right, K, vertical, up, down. So we're going to look at our first two here. So we're not going to graph it, but we do have g of x equals x minus 4. What is its parent function? What group would this be part of? Constant, quadratic, linear, absolute value. Not quite. So quadratic, the main key of it is the power of 2, yes? Does our x minus 4 have a square? It is linear. Now, technically, this is part constant, because the 4 is a constant term. But we give an equation the highest order. Not a highest order, I don't know if that's technically the correct phrasing, but the x to the first power is linear, is a linear term. So if we had an x squared plus x minus 4, we had an x squared added to it, it would be quadratic, because the x squared is quadratic. So here, x is linear. Does that make sense why it's linear? Yes? No? Okay. So it's linear. Now, we're going to graph this. Now, for the most part, graphing is helpful, but in our current era and where we're at, being able to know 100% how to graph is helpful, but I wouldn't say it's absolutely necessary. Because I will say the most irrelevant statement. I've said it a few times today, because I've heard it, especially when I was in middle school, high school, especially from our math teachers. You will never have a calculator in your pocket, so you need to know how to do this. That statement can become completely irrelevant, because all of our phones have become 100% a calculator. And if we don't have one specifically on it, we can download it, we can pull it up. There's Google, all of it will do it now. So essentially, we've actually come to an era where we do actually carry a calculator in our pocket. But with that, being able to 100% know how to graph, there's 100 different places that can graph. So having a full understanding of how to do it and how to read a graph, yes. But knowing exactly how to do it is not as important as it used to be. Because here, and I will show you all how to use these. These are the 84, the graphing calculators. They're going to be over there when I pull them out and actually take the time to get them out again. This here is our linear function, our parent function. Now, the one that they gave us is x minus 4, yes? Graph it. So what happened from the blue graph to the red graph? So blue is our parent, our f of x equals x. And our g of x equals x minus 4 is the one in red. So it looks like it could have gone over 4, but really it went down 4. And if we look at the table, so at 0, it's now at 4. It was at 1, it's now negative 3. So it went down 4. Now, linear is a little funky because here, for the most part, down and up, left, right, up, down, kind of get a little similar. But here, it just went down 4. Okay, so we kind of get how that worked, yes? Graphically. Now, let's look at this algebraically. Our general form, a parentheses x minus h, close parentheses plus k. We have this here, yes? Do we have any parentheses written for g of x? No, it's just x minus 4, right? Technically, we could put parentheses around the x, but what that's telling us is that there is no h. H is 0. H is not there, so there's not a movement left or right. But that 4, that minus 4, is taking the place of k, yes? K tells us that it's going to move the graph up or down. So what is the value? So 4 is what we have, yes? And since it is minus, yes, it would go down 4. And that's what we saw graphically, yes? Algebraically matches up. We good with this here? Good with this so far? Yes? All right. Let's look at the next one. This one here, g of x. Which group is it a part of? Absolute value. This is one of the few ones that's, I can't read the function without giving it away, because we would say that g of x is equal to the absolute value of x plus 1. So what group? Yeah, it's got the absolute value. It has the absolute value. Almost reading what the function is, essentially told us what the function is. So we have this here. Now, I think y'all remember geometry, algebra 1, we can't type an absolute value into our 30xs, the yellow calculators, which stinks. Now, the graphing calculators, We can do absolute value. Absolute value of x. Give us the graph. Now the one that we have, and again, I'll go over how to type this in when we start, and we'll start using it and going over it. And once I get them out, y'all can follow along, so we can start learning how to use the calculators. One of the nice things about the 84s is these are approved to be used on the ACT. Pretty much all standardized tests let you use the TI, these 84 plus graphing calculators. Yes.
Jonathan, you didn't know that?
Well, not every subject.
Yeah, science,
Math, history, or English and reading. So it goes English, math, reading, science.
So you're four.
Does our school for the ACT give us the written test or no?
Mm-hmm. For the ACT you'll take in the spring, yes.
Written test for what?
So you get an essay prompt.
Uh,
So I think y'all all have Miss Sites. She will go over that. Okay. But yeah. But talk with her. She can help give y'all some prompts and help y'all with that. They will give you a prompt and you have to write an essay about it. That's it. 40 minutes.
How long is it? It sucks for me. I get writer's block.
5 paragraphs.
my first assignment that I've done concurrently, I had to do a 50-question assessment, and then, like, you're supposed to read this thing, but I can't find this book.
Yep.
Told you about it, and I get on there, I was just, like, looking at it, and then it's like, it locks me in, and I can't, like, click out of it or something. It's like, you have 4 minutes, go! And then the clock starts going, I'm like, crap! And then I scroll down, and then I'm like, there's 40 questions on this? Just reading the questions and doing it. I finished it with less than a minute left. It's just, no. I did not pass.
Now with the essay part of the ACT, the prompt, guys, so we'll say this and then move back into this. The prompt does give you some discussion or kind of ideas that are for the prompt, some that are neutral, and some that are against. So it gives you all 3 sides, and then tells you to use that and go. So it does give you a starting point. Now, if we look at this here, the blue graph is the parent function of the absolute value. The one in the red is the new one we have. How did it move? It went to the left one, yes. So the transformation is left one. All right, now let's look at this algebraically. So, f of x equals a times absolute value of x minus h plus k. Well, there is no k value, yes? Because there's nothing being added outside the absolute value. What's our value of h? 1. So h is 1, so it's telling us we're moving 1 unit. So h inside is left to right.
Oh, that's horizontal.
Horizontal.
So you're going right.
But what did the graph say? The graph said left 1, but it looks like it's right 1, yes?
Well, yeah, left is negative, right?
Yes. Now, and there's a reason I pull this out. Look at the general form. It is what? X minus h, yes? The one we have is x plus 1, yes? What is the only way that we can turn a negative into a plus? Is with another negative. So really, what this function is saying is that g of x is equal to the absolute value of x minus negative 1. So the value of h really is negative 1. That's why it's moving left. So we could do this each time and try to remember that. Or anytime we have these horizontal translations, left, right. Or, and we'll get to this probably on Friday. Horizontal stretch and shrink is going to be the opposite of what we think. As plus 1, again, we think it should be right, but it's actually moving left. And if we had x minus 1, minus, we think left, but it's actually to the, anytime we're inside those absolute values, it's going to be the opposite of what we think. As a horizontal stretch, yep, it's going to look like it's going to be a stretch, but it's actually a shrink. And some of the horizontal shrink is going to look like it's a stretch, but it's actually a shrink. Absolute values. The only one that doesn't do this is reflection across y, but that's, is there a negative there? And we'll get into that here in a minute. Questions on this here? Well, reflections. A reflection is a transformation that flips a graph over a line called the line of reflection. A reflection is the same distance from the line of the reflection as the original point, but on the opposite side of the line. I've done these in geometry, where you redrew the shape on the other side, and we did the reflection. Now, for us, one of the reflections that we'll have is going to come from the A, not the number or the numerical value of A, but its sign. If it's negative, if the A is negative, it's a reflection across the x-axis. Nope. That's just, there is no reflection. So if the A value is positive, there is no reflection. So if A was positive 2, the 2 does not attach itself to reflection. That's vertical stretch or shrink. It's something else. But if that A is negative, then it's a reflection across the x-axis. Now, it's not going to be too much in this lesson, but I'm going to write this in. You don't have to write this in at the moment. But where I put that B value, or that B there, if that location is negative. So if the sign in front of the x inside those parentheses or absolute values is negative, then it's across the y. So,
Two on the sides. It's crazy. Math is about number, right?
yep.
The two on the sides, there is a single number. It's all letters.
Yep.
I missed like 5. Yeah, well, there's not a single number.
Yeah.
Yep. Upper level math, there are some things, I've done several problems and not written a single number.
How is it math?
But,
The alphabet.
so the B, where B is, if that spot has a negative, if that is a negative, then it's a reflection across the y. But we're not going to worry too much about that at this point. If that A, if it's a negative, if there's a negative where A is, then it's a reflection across the x. If there's just a number, 1/9, that's not a reflection across the x. That's
Negative.
if it's a negative 1/9, there's a reflection across the x, and then the 1/9 is attributed to our vertical stretch and shrink. We're going to get to that tomorrow, the vertical stretch and shrink. And specifically, if we look at this first one here, P of x equals negative x squared. The x squared tells us it's connected to which one? Quadratic.
Yeah.
Quadratic.
Well,
It's a quadratic. Now, the general form for quadratics A times x minus h squared plus k. Well, there is no h value because there's no parentheses, so nothing being subtracted. Or added to x inside parentheses. Nothing's added or subtracted outside. The only thing we have is the negative. So our A in this case is negative. It's technically -1, so it is a reflection across. Yes. Reflection across the x-axis. It is.
Supposed to be freaking chicken patty day and waffle Wednesday, but no. It's
I was kind
Friday
of upset
now.
about the waffle thing.
It's Friday now. It's pizza and biscuits and gravy. That makes no sense. Biscuits and gravy is weird. They've had breakfast for lunch. It's not normal. What? That was for breakfast. Biscuits and gravy was for breakfast. Oh, I got it.
I
No,
was
why
upset
not?
about that. They gave me the tiniest piece of pizza I've ever seen.
Yeah, I got the last piece that was tiny. I should have just done the freaking avocado bread. That sounds good.
Well, all right, guys. So this here is our parent function, the quadratic, x squared. So the one we had was negative x squared.
So it just literally just
Flipped it. Yes. Now, as we've said, inside the parentheses, because if it was parentheses negative x squared, this would be across the y-axis. Yes? Now, the one in blue is our normal one. The one in black will be the reflection across the x-axis. Okay? You need to pay close attention to what this thing graphs, because it's going to be quick. Yep. Because all the points to the right of the y-axis for the original one, it flipped them, so now it's on the left side. And it took all the points to the left of the y-axis and put them on the right. So it reflected across the y-axis, and you got the graph back.
oh, so it like turned them like this.
Yep, it's pretty much the same as if you look in a mirror, because it's technically a reflection. So it's flipped, but it's, since our phasors are symmetric,
So kind of like
it looks the same.
they're sitting there like this and it rotates.
Yes. The only way we'll see a difference is if we move it away from the, oh, let's turn this one off, graph. So I moved it 1 unit to the left. And if we reflect that across the x-axis, or across the y-axis, we have the +1. Now it's flipped to the other side. Because if that center's on the y-axis, it's not going to change it. It's going to look the exact same.
Oh yeah, it's kind of like that.
Let's look at this one here. K of x equals negative x. What?
It's gonna be.
You gotta stay constant, right?
Yeah.
Linear.
Nope. Linear.
Oh yeah, good job.
Constant would be if it was k of x equals 4.
Oh.
Constant is a number. There are no variables.
If it says equal and then like x, it's gonna be
Linear.
okay.
If there's a power of 2, it's quadratic.
Quadratic.
So it's gonna be like constant is just all real numbers.
So constant would be f of x equals 2.
Okay, so it just has
So
to be
it
It's just,
takes a number.
it's just a number.
Okay. So linear is always x.
X, yep. General form, f of x equals a parentheses x minus h plus k. Well, we have no h and k, so it's not moving up, down, left, right. But the a in this case is negative, yes? And since the a is negative, it is a
Reflection across the. So what about the negative? Oh wait, no, I see. K of x equals negative x, f of x equals negative x.
Yep, so it's different. So h of x, k of x, f of x, g of x, it's just different ways to name the function. Because k of x, all of them really are taking the place of y. Because it's really our normal y equals mx plus b. F of x is the same as y. K of x is the same as y. Because we use these different ones so that I can say we're going to apply this to k of x. and we know immediately which one we're talking about. We can see it and apply that to it. Where if they were just both y and we're saying we're apply this equation to y, the y equation, well, they all have y. There's no way to distinguish. So the main reason we use this function notation is distinguish one function from another. So we can talk about more than one function at the same time and not confuse them. Questions on this here? We have 3 more that we're going to do today, and we'll finish this tomorrow. Number 2, g of x equals x plus 3.
That's the C. No,
If the x wasn't there, if it was just g of x equals 3, then it would be constant.
So f of x equals a.
Now, I will say this. If you want to write those each time, go for it. If that is helpful, write them out so that we can see what connects to what. If you don't need it or it's not helpful, you don't have to.
So it would be g of x equals x.
So,
Then what would the plus 3 be? K?
so the plus 3 is our k. K moves it which direction? Up, down, left, right? Up or down, yes? How far are we moving? 3.
3 up.
And since it's positive, we're moving up. Since it's plus 3, positive is telling us moving up 3. Because if it's outside the parentheses or absolute values, it's exactly what it looks like. Plus 3 is up 3. The next one, h of x equals, it's quadratic because of our power of 2. Now I'm going to go on and write this out. So, do we have a k value?
No.
No, technically yes, but no.
Well, yeah, it's just the power.
Well, the power of 2 is what tells us it's quadratic. The value of k technically is 0 in this one.
Not k, you're worthless.
So, because we're moving it neither up nor down, it's 0. So we don't write plus 0. So there is no up or down. H tells us we do have a left or right. Yes? And it would be indeed be right 2. Because with left or right, it's always the opposite of what we think. Because since it's minus, it looks like it should be left, but it's actually to the.
The next one is absolute value.
Yeah.
Can I have a sticky note? I need a sticky note.
Yes. You need it to be sticky. Yeah. Absolute value, a times x minus h plus k. So h and k, there's not one. So there is no left, right, there's no up and down. But the a is negative, so it is a.
If I had a cursive, yeah.
I see how it is.
And it'd be across the.
Wait. Cool, I'm trying to.
X-axis.
Left turn is not going to mimic mother's handwriting.
Not my mother's. So what is that? Right after? Oh, those are the absolute value bars.
Yeah. The first one came out a little slanted.
Oh, then you're going to get right slop with this. Kara's the only one.
Questions on this here?